This is Tech Math 2, and we're going to do section 9.3 and 9.4 today. In section 9-3, first thing we're going to start with is rules. And if we apply the rules, then everything will be fine. If I take the log, and it doesn't matter what the base is, of two numbers that I multiply together, that's the same as taking the log of that same base, whatever it might be, plus the log of those two numbers. So this might be base 10, or it might be base 2, or it might be base whatever. It doesn't matter what it is. A has to be, well, I'm going to put an A here, base A. We can't have a base that's less than 0, so the base has to be greater than 0, and we can't have a base equal to 0, and we can't have A be 1. Now, why can't we have A be 1? Well, if the base is 1, and I say 1 to the n is equal to 24, what is n? Can't get there from here, can we? All right, so that's why A, the base can't be 1, and the base has to be greater than 0. So it could be a fraction, that's fine. It could be 3,587, that's fine, but it can't be 1. All right, next rule. If I take the log of something divided by something, and I guess I misspelled log, and again I'm going to be in base A, then it's going to be the log of the guy on top minus the log of the guy on the bottom. Again, A has to be greater than 0, A cannot be 1. Alright, turning the page. Next rule. If I have log of any base of something raised to some power, then that's the same as that power that I raised it to times the log of whatever the base is times m. And if I take the log of the nth root of something, well, that nth root of something is just something raised to the 1 over n, so obviously that would probably be 1 over n log am. And these two guys are telling me the same thing, because b could have been a fractional number. It didn't have to be a whole number. The log, way to go. The log base A of 1 is going to be 0, and the log, we're not done yet. I said and, but we still have another one. Well, this could be written as log base A m to the minus 1, right? It could have been. So log base A 1 over m is going to be minus the log base A of m. All right, turn the page. The log base A of a to the x is going to be x. This is going to be important, because if we have something like e to the 2x plus 5, and I take the natural log of it, then that's just going to be 2x plus 5. So that's going to be a way to get rid of exponentials. And if I had 10 to the 2x plus 5, and I took the common log of it, then I'd end up with 2x plus 5, and I'm going to be using that often to solve problems. And a to the log base A of x is going to be x. And there's not much difference between that and if I take log base A of a to the x is equal to x. So those two things are about the same in what they're trying to tell us. So if I have something, I'm solving a problem that says log base 1.2378 of x cubed. If I had something like that, then I could say, well, I'm just going to raise this to the 1.2378 power, and I'm going to end up with x cubed. So and it allows me to drop my logs or get my logs back or whatever it is. So that comes to the issue n factorial. So 2 factorial is 2, and 3 factorial is 6. What is the log of n factorial? Okay, so we take out our calculator and we go 66 factorial, and we get a number. And we go 76 factorial, and we get an error. So somewhere between 66 and 76 factorial, our calculator can't do it. So if we wanted the log of 76 factorial, how would I do that? Well, I know I can do the log of 66 factorial. So I'll do the log of 66 factorial. Log, where's my log button? There, log 66 factorial. And I got 9.27 exponent of 1. And then I'm going to think, well, what is 76 times the log of, no, 66. What's 66 times the log of 66? 66 times the log of 66. And I got 1.2 exponent 2. And I say, well, these guys are real close to each other. So if I want to find the log of 76 factorial, which I can't do because my calculator is not going to do it for me, I can say, well, that's about 76. About 76 times the log of 76. All right, so 76 times log 76. And I get 1.4 exponent 2 and say, well, that's close enough. So what do you think about that? Yeah, I know, you didn't want to know that. Okay, so we'll go back. So but if I have a huge factorial number, that's the way I approximate it. Okay, so now we're going to go and do problem number 1. And we're going to write the expression as a sum of or differences of multiples of single logarithms. Now the instructions are written in English, right? 5x squared y. So we're going to say that this is log base 2 of 5 plus 2 log base 2 of x plus log base 2 of y. Okay, so all we did is the rule that says if I multiply them together, it's the same as adding. The rule that says if I take an exponent, that's the same as multiplying. I go and apply that, and now all I have is sums and differences of, or multiples of, a single log. All right. We'll look at number 3. I'm doing the same thing. I've got the log, and we have a 10 there, so I'm not going to put it down because we normally don't write 10. Y cubed z. All right, so we just say, well, gee, that's going to be log 2 plus 2 log x minus 3 log y minus log z. And all we did was apply the rules we had. If I'm dividing, it's a negative thing, and if I'm adding, it's a positive thing. All right. Look at number 10. Log base b 1 over z squared. Okay, cube root of x squared over y. All right, so I'm going to have log base b, 2 log base b, minus 2 log base b of z, plus 2 over 3 log base b of x, minus 1/3 log base b, way to go, way to put a base b of y. And then I'd rewrite it and put the negative sign in the end and put the positive guy first, but won't bother today. Okay, number 13. Am I going fast enough? Number 13. Log base b. We want something that log base b I can't do in my calculator. I want something I can do in my calculator. Plus 1 divided by square root of x plus 2. All right, so I'm going to have 2 log base b of x plus log base b of x plus 1 minus log minus 1/2 log base b of x plus 2. Okay. Now we just broke everything up. Now we got to put them back together. So this is the put them back together group. All right, number 13, number 16. 16. 2b, 2b. 2b or not 2b? That's the question. Log base b of z minus 3 log base b of x. And we want to make one thing. So we want to make one thing. Log base b of something. Z squared divided by x cubed. Clear as mud? Number 17. I got log base b of x, 2 log base b of y, minus 3 log base b of z. I want to make it into one thing, log base b. What is it going to be? Okay, I got an x on top, I've got a y squared on top, I've got a z cubed on the bottom. Well, I guess we should do 26. That looks like fun. Number 26. 1/2 log base b x plus 1. 3. What is this all about? Log base b of x plus log base b x minus 1. Don't even have enough room to write the whole problem down. That's really bad. Log base b 2x minus 1. Well, assuming that I wrote the problem down right, which I didn't do, because the bracket goes there, it doesn't go there. There, now we have a chance. All right, so I want 1 log. Okay, so I got log base b of, I'll go with the square root of x plus 1. I got a minus sign out there, so this is all this other stuff's going to go on the bottom. So I'm going to have an x cubed on the bottom, x minus 1 cubed on the bottom, and a 2x minus 1 cubed on the bottom.
When, on that first part, I mean, it's a half log b, base b.
Yeah.
Once you do to the second root of x plus 1? Or, no, I'll be first. So wouldn't you still square x plus 1 though?
No, it's 1/2. It's raised to the 1/2 power. X plus 1 to the 1/2 power, which would be the square root of x plus 1.
Okay.
Yeah. So this guy here, yeah, that guy there would be log base b, x plus 1 to the 1/2, which becomes the square root of. Okay, maybe we can do these on our calculator. Maybe we can't. Number 28. Log base 2, 2 to the 5th. That's 5. That's okay. 29. Log base 3 of 3 squared. Oh, wait a minute. I didn't put a 9 there? Bummer. Yeah. If you don't recognize the 9 as b squared, then that'd be bad. 30. Log base 2 of 2 to the 4th is 4. Might as well do 31. We're on a roll. 31. Log base 5 of 5 cubed is 3. All right. 36. Log base 10, but normally we don't write a 10 there, of 1 over 10 minus 1. Oh, that one I can do in my calculator. It's log base 10, right? So I can go log, where's log? Log 0.1. Boom. Oh, wow. It's minus 1. About time. I knew I could find something that worked on my calculator. Might as well do 38 while we're at it, right? 38. Log base 10 of 1 is 0. And that one works in my calculator too. All right, number 4. 3 log base 3 of 9 is 9. Right? Because the log 3 base 3 is 2, so this becomes 3 squared, which becomes 9. And yeah, that's what that is. Ooh, 41. 2, 5. 5 squared log base 5 of 6. So that's going to be 5 log base 5 of 36, which is going to be 36. Now, in a different section, we're going to learn that log base 5 of 6 is log 5 divided by log 6. Okay, so this problem we can just put in our calculator and we can say 5 raised to the 2, that's not a 2, that's not a 2 either, 2, well, I'm going to put a parentheses, 2 times log 6 divided by log 5. Oh, 36. Yeah, the calculator told me it was 36. So we have a way to work that problem without being in this section because our calculator will do it. But clearly 5 raised to log base 5 of 36 has to be 36. So that solves that problem. We'll do 46 and then we'll move on to the next section. Oh, come on. You got to be kidding me. Log base 4 of 16 raised to the log base 4 of 64. Again, I can just put this directly on my calculator. It's going to tell me the right answer. But anyway, so this is log base 4 of 4 squared times log base 4 of 4 to the 4th, 4 cubed, right? 4 cubed. Okay, so Log base 4 of 4 cubed is 3. 3 times 2 is 6. So the answer is going to be 6. All right, now I'm going to put it in my calculator. Log, okay, log, thank you very much, calculator. Log 4 raised to, no, log 4 of 16. Log 16. Log 16 raised to, log 16 raised to parentheses log 64 divided by log 4 close parentheses divided by log 4. 15.37. Shit. Enough of that calculator. Alright. Obviously I put it in wrong. So did I do it right? Log base 4 of 64. So that's 4 cubed. Right? That's 4 cubed. Is 3. 3 times 2 is 6. Log base 4 of 4 raised to 6 is 6. Alright, well, we'll go with that answer. Okay. Now we're in section 6-4. And all we're going to do is talk about common logs. So 10, the log of 10 raised to 3.75 is going to be 3.75.
Section 904.
You want to be in 9-4? Typical. The class decides they want to be in section 9-4. All right. Okay, well, we can do that too. It doesn't matter that much. Okay. All right, turn the page. Is there anything there? Nope, nothing there. Okay, so yeah, there's some theory there, but we'll work some problems and get through the theory. All right, so that's what we're going to deal with. Okay, so number 2, the log of 928. The only way you get that is put it in your calculator and ask for the log of 928. You expect it to be some number less than 3 because log of 1,000 would be 3, right? So when this comes out to 2.9675, you're perfectly happy with that. Now this says 4 significant digits, 1, 2, 3, 4. Right, so I would round that up to a 8, because that's the type of guy I am. Number 3, the log of 45. Now we'd expect the log of 45 to be something less than 2. So log of 45, 1.653. 1.653. Now, if we take 10 and raise it to the 1.653, what do we expect to get? The class says 45. Now, if I take the answer in my calculator, which is 10 significant digits, that's what I'm going to get. So I'm going to go 10 raised to the answer, and I get 45 exactly. But if I go 10 raised to the 1.653, I end up getting 44.9779859. And if I round that out to 4 significant digits, 1, 2, 3, 4, that rounds up, and I end up with 45, right? So if I, that's why I go to 4 significant digits in my log, so I can get back what I had. If I don't, then I'm gonna be too far away. All right, so that was 3. Guess we'll do number 12 next. Well, let's do 8. We'll do 8, then we'll do 12. 8. Log of 0.0000497. All right. Log 0.0000497. Minus 4.304. Minus 4.304. And then we'll do number 12, log of 1. And we better know what that is before I even write it down. Log of 1 is 0. All right. So now we're going to do anti-logs. We're going to go the other way. All right, well, that's fine. Number 13. Going to go the other way. We know that the log of n is minus, no it isn't, it's 1.4048, and we want 3 significant digits. So we raise both of these numbers to a power of 10, and we say n is equal to 10 raised to the 1.4048, and we only want 3 significant digits, so we'd write down 2.54. No, we wouldn't, because the exponent says it's 1, so we'd call it 25.4. Okay, that's because my stupid calculator is not in floating point. All right, we'll move on to 17. The log of n, 0.2782, and we're hoping that when we get done, we have some number. All right, so I'm going to raise both of those to the 10th power, and put n is equal to 10, raise the 0.2782, and we only want 3 significant digits, 1.90. We'll do number 24 next. Do you see a pattern yet? No, you write something down, you pick up your calculator, you write down the answer. See that pattern? All right, log n minus 6.813163 raised to the power of 10, and is going to equal 10 raised to the minus 6.8163. Boom. 1.53 times 10 to the minus 7. All right. Now we get to find the values of these guys rounded off to 3 significant digits. All right, so number 26. Log 984 divided by log 4. And all we do is put it on our calculator. Log 9.84. Way to go, there's no point. 984 divided by log 4. 2.16. How many significant digits? 3. Okay, 2.16. All right, well, that's reasonably okay. 28. Log 64.5 divided by log 207. All right, log 64.5 divided by log 207. 0.339. Okay, moving on to number 3. You know, I'm not even trying to do these anything other than pick up my calculator and put it in. There's no simplification I can do. There's nothing I can do to make it better. Well, what's the problem? What do you mean you're not getting any of those answers?
Like 26, I got 4.97 there. Then I tried it again without the parentheses, and I got 3.21.
Okay, so obviously you're hosing something over. So what you should be putting in your calculator is log. There's a parentheses, it's automatically there, 98.4, close parentheses, divided by log 4. Like that. Now, you don't have to put that guy in, but you could. And you're telling me that you're not going to get 2.16?
No, I get 4.97.
Right here. Oh. Well, if you would have done it wrong like I did, you would have got the wrong answer. But no, you had to do it right. So if you put log 984 divided by natural log 4 in your calculator, I'm sure you're going to get the same answer I do. I'm sure that's going to happen. Okay, so how far back do I have to go?
26.
26. All right. I will try again. Log. There it is. I found my log key. 984 divided by log. Got to hit the button twice. 4. 4.97. Is that better? 4.97. I wasn't even trying to get it wrong. Did I get 28 wrong too? Yep. All right, log 64.5 divided by log 207. And 0.781. Is that better? So let's see if I can get 30 right the first. Anybody have the answer to 30 so I don't have to put it in my calculator and get it wrong again?
0.8233.
0.8233. Anybody agree with that? That's obviously wrong, so we'll cross it out. Huh?
Yeah.
That's obviously wrong. I have to put it in my calculator. Log 8 divided by the log of that guy there. Okay. And so the right answer 0.823 because they only want 3 significant digits and Ben gave me 4, which made it obviously wrong.
Classic mistake.
Just like on the physics test yesterday, I showed you or last Friday, I showed you that problem with the inductance, for the value of L. I didn't show you the test. The test was obviously a 2 significant digit answer, and the answers there were 3 significant digits, 3 significant digits, 2, and 1 and 3 significant digits. The obvious answer is the only guy there with 2 significant digits, and the problem's really hard to do. So anyway, that's just one of those things. You have days like that. Well, I don't know about 40. I guess we'll do 40. I got the log of 2 things added together, right? So I'm going to change that to the log of 276 times 98.4 divided by the log of 2 divided by 14.5. And that'll have less strokes in my calculator and less of a chance of me getting it wrong, although there's always that chance. 276 times 98.4 divided by log 2 divided by 14.5. And I've got minus 515. Minus 5.15. Okay, anybody agree? Now, anybody in chemistry? Okay, so we don't care about the pH problems, but we do care about decibels. So the sound intensity, the intensity of the sound level defined in example 5, compute beta. Okay, so that's what we're going to do. We're going to compute beta. Number 48. All right, so example 5 says that beta, which is also a number in dB, but it is 10 log the number 10 to the minus 6 watts per centimeter squared divided by 10 to the minus 16ths watts per centimeters squared. Okay, well this looks like 10 to the 10th. So the log of 10 to the 10th is 10, and 10 times 10 is 100. So this would be 100 dB. Now is that power or is that voltage? Are we dealing with power or voltage? We're dealing with power because it's 10 log and not 20 log. If it was voltage we're dealing with, the dB would be 20 log, whatever I have divided by whatever I have. Plus I have W's here for watts, which is a key giveaway for power as well. Okay. We'll do 48. We just did 48. Okay, we'll do 50. 50. And now we have B is equal to 10 log 10 to the minus 9th divided by 10 to the minus 16th watts per centimeter squared, watts per centimeter squared.
Okay, what are we getting at 16 at real quick? Just so I know.
It's by definition. So it's intensity divided by intensity naught. And intensity naught is defined as 10 to the minus 16th watts per centimeter squared. So that's the least the best human ear can hear. So on page 317 it says intensity naught is the intensity of the threshold of hearing. So if I was up here, no matter how low I went, you could still hear a pin drop as long as it has at least that many watts per centimeter squared hitting your hearing. And of course, most of you have listened to loud music too much of your life. You can't hear that low anymore, so don't worry about it. You're not even close. But back before TV, before radio, when we were doing the testing in the 17 and 1800s, the general population that didn't do things like shoot cannons on ships or something could hear. That'd be their threshold of hearing. Your generation threshold of hearing is probably somewhere around 10 cubed or something like that. No, just kidding. No. Some pretty big amount though. About, yeah, maybe 10 to the minus 12. Maybe you only lost 4 orders of magnitude there. Previous life or whatever. Okay, so that's where it comes from. It comes from the definition. And if this were going to be watts per meter squared, then that would be 10 to the minus 12 watts per meter squared would be intensity naught. All right, so back to what we're doing. 16 becomes positive 16. Subtract 9 from 16 becomes 7. Log of 10 to the 7th becomes 7, and I become 70 dB. Okay, back to number 51. How can we go back when we haven't gone there yet? Number 51. Power naught is 12 watts. Intensity naught is 0.5 watts. We want to find we define electrical power and gain in dB. Okay, so now we're not talking about the intensity hitting the ear, we're just talking about power and gain in general. That's going to be 10 log power in divided by, power, the other way around, power out divided by power in. Power out divided by power in. Just like I do 10, 20 log. 20 log voltage out divided by voltage in to find the dB of the voltage, how much there's there. Okay, so that's what we're doing. So we want 10 log 12 divided by 0.5 watts. 10 log 24. All right, 10 log 24. 10 times log 24. 13.8 dB. This is the problem the guys are having in physics right now. They're making these wind generator things, and their power in is huge. They got a 8 horsepower fan blowing air onto their windmill thingy, and they're getting little itty bitty stuff out. But that's all caused because of the gear that they had to deal with. Okay, last problem, number 54. Power out 1 watt. Power in 1.2 watts. Well, this is good. This makes it so I don't have much left over. 10 log 1.0 divided by 1.2. Okay. 10 times the log. 1 divided by 1.2, close parentheses, minus 0.792 dB. Doesn't say how many significant digits, does it? So we should only keep 2 significant digits in our answer because that's all we got. Okay. Minus 0.79 dB. Okay. Tomorrow we get to do everything all over again using our natural log key, which I already used on my calculator today to get the wrong answer for. And we'll just do it over again and continue solving. Okay, good enough?